Begin off today, we'll talk a little bit, we'll just touch up on a little bit of the complex analysis that was pending from last time. And then after we finish that, we'll just look at a couple of examples and look at more, we'll just try to form a theoretical understanding, a clearer theoretical understanding of complex analysis, and look at one last result, and then we'll just move on to discussion of the Feynman propagator and time ordering, and essentially that whole thing will be the main focus today. Before that, let's just look into the Cauchy principal value. This is not directly relevant to the propagator that we will be discussing, but it's nevertheless a very important result that we have, okay, or a very important idea rather. So let's look at an integral, a real integral from minus a to b, where a and b are strictly positive. So you have a strictly negative number to a strictly positive number of the form integral of 1 over x dx. Okay, now we can obviously at x is equal to 0, we have a singularity, right? So we cannot, this integral is not defined because we have ln 0 bit. So we have ln b minus ln a plus ln 0 minus ln a, ln b minus ln 0 plus ln 0 minus ln a. So that's the whole thing that we have. So essentially what we can do here is we can, so how does the graph look like? So how does this look like? So 1 by x is something like this, right? This is x, this is 1 by x, right? So you have something like this. So this is how your graph essentially looks, and when you integrate it, you want to integrate it within this region. So note that this is not a bound curve, so you don't have a very you don't if you don't fix some sort of a bound, you have a very weird notion of an integral. So essentially you can just have this whole thing, and then the integral just blows up to be just infinite, right? So essentially what we need to do is we need to be a little careful while dealing with around 0, right? So what we can do here is we can very cleverly say that this integral can be broken down to two examples, right? So we can say this is the limit as delta tends to 0 from the positive side of integral of minus a to minus delta. So you have minus delta here, and then you have some a here, minus a here, and then you have b here, and then you have some sort of a positive delta here, right? So that's, so we are dividing our integral domain into sorry for that now. Anyway, so we are dividing the integral region into two domains. One is this and the other is this, right? So now given that we have this, what we can do is this so we'll just write it down by x plus integral of a to delta to b of 1 by x dx. So obviously the limit holds for the whole integral, right? So then we can essentially what we are so essentially if you look at this, so at x is equal to 0 you have two values of plus and minus infinity. And then what we are doing is we are saying that in some way we are analytically continuing the function at both plus and minus infinity, like at x is equal to 0, and then we are just forcing it to 0 because like we are somehow like just wrapping it around at 0. So from plus and minus infinity it just jumps to 0, so we are just sealing it off in some way. That is one intuitive picture that I can think of it. So this, if you look at this integral, when you solve it you get essentially ln delta minus ln a plus ln b minus ln delta, so which is just the evaluation of the limit. So now your delta plus and delta plus and minus delta, which is ln delta, just cancel out and then you have 0. So you in the end you have just ln b minus ln a, right? So given this, let's just, so this is okay, so let's just take the example, like let's take another example, right, to see exactly how this is not perfect. So we're actually doing some mathematical jugaad over here. So let's just take two deltas instead of defining one delta like over this thing. Let's just say this as delta 2 and this as delta 1, right? So then so this is delta 1 and this is delta 2. Just a matter of convention, it doesn't really matter, we're just trying to prove a point here. So let's just take this as integral from minus a to minus delta 1 plus integral delta 2 to b of 1 by x dx. And let's put the limit delta 1 comma delta 2 tends to 0, just positive, just some small positive number. So we have here, so this is clearly negative and this is clearly positive. That is why we have like delta 1 and delta 2 approaching 0 from the positive. So it's a very small positive number. So then so let's just take delta 1 is equal to n delta 2. Okay, so when it comes to x, the variable itself and the integral, delta might be infinitesimal, but we cannot really fix a relation between delta 1 and delta 2. I mean, like in the sense like we can fix some arbitrary constant from delta 1 and delta 2, and that doesn't really change how small delta is. Okay, so then you have like so the idea is it's a perfectly logical thing to do, to say that delta 1 is equal to n delta 2, whereas so a small number is equal to n times a very small number, a very small number is equal to n times a very small number. So it's like saying 0 is equal to n0, something very similar, right? So we're just taking to the limits there. So then we have, when we evaluate the same integral, we have ln of delta 1 minus ln a plus ln b minus ln delta 2. So then what we have is, this can be rewritten in the form of ln b minus ln a minus ln n. So when you say fix the relation between 1 and delta 1 and delta 2, when you take this difference, it becomes ln n. So now this doesn't really make sense, because this shows this ln n, if we are more mathematically accurate in terms of like talking about our delta 1 and delta 2, right? If you just don't force them to wrap together at 0, and if you just say that okay, delta 1 can be different from delta 2, like in the sense there is some a more continuous, or like a smoother mapping, a more analytic consideration of the interval between 1 and between the two sides of 0. So we have ln n, which is clearly divergent. So as n blows up, your ln n will also blow up, and your integral, the value of your integral, is essentially it's divergent. So but however, that can be subverted, okay, with like so if we just generalize this whole principle of just taking avoiding this whole thing and just taking the limits here, we got a perfectly reasonable integral here, right? We got a perfectly reasonable real value here, right? So to get the same to get some value out of integrals with singularities or with poles, so what we can do is we can take the limits at as it approaches the singularity. So suppose you have a singularity at x0. Yeah, so then you can just take this as the integral of so you can just define a principal value. So this is written by the integral sign with a cross in it, or you can just another way of writing it would be just having an integral and then call it p, like fixing a letter p before the integral. Yeah, so these are equivalent. So essentially this can be rewritten as limit as delta tends to 0 plus integral of some, so you have some lower bound, x0 minus delta and f of x dx plus integral of x0 plus delta. So then you have another like random upper bound, f of x dx. So yeah, obviously the upper and lower bound can go from plus and minus infinity. It can just be anything, right? So this is called as the this is the Cauchy principal value. So it just says that you can take if there is a pole, there is a simple pole at a single point, you can just consider the integrals outside the pole, two separate, like divide it into two separate integrals, and it can still have be valid, right? Like you have a principal value. You don't have the accurate like net integral, but you have a principal value. So you have some sort of a real what I say. It's not necessarily a continuation, but rather a real approximation or like of the integral. Now again, approximation in the very loose sense, right? Because you don't really you can't approximate infinity, but then you just somehow, right? Yeah, so you just have a principal value there, right? You just want to get a number out of the whole thing. So now let's go back and then let's try to look at the Laurent expansion. If you remember last time, let's take a Laurent expansion of a function with a single singularity. So if you have f of z such that is singular simply at z0. So then we have the Laurent expansion for f of z will be equal to some sort of a polynomial in terms of a minus 1 z minus z0. So this is essentially the like it's a function of z. A is a function of z. When you calculate the residues, remember last time we spoke about this, right? So when we like try to calculate a residue last time, so if you have f of z by z minus z naught, and then integral dz is equal to essentially f of z times I to I, right? So this is what we figured out last time. So similarly, we are using the Laurent expansion to cover a complex, to expand the complex function into some sort of an approximate polynomial where we have let me write this clearly, right? So this is a minus 1, okay? So z minus z naught, it has a single pole, plus a naught plus a1 z minus z naught to the power of 1 plus so on a n z minus z naught to the power of n plus so on. So this is your Laurent expansion. So essentially the idea is that you can get your the residue in terms of a minus 1. It gives you the coefficient for the residue. So for example, if you have a singularity here at z naught, okay, then you have like a contour integral around z naught. So you have some sort of a contour around z naught. So this contour can be reduced into two parts, right? So it can be, so if you say, if you draw a small circle, so if you, the idea is if you can split this into two semicircles, and then take the contour integrals around that, you have two different regions, right? You have one and then you have 2. And note that because these two regions don't have like any singularities or opposed by by Stokes theorem, and essentially so we discover that the whole integral here will be 0. Okay, and we only need to evaluate things around this one singularity. So taking this one singularity, right? So we can we can represent a smaller, like we can represent the cutting around the singularity in terms of two semicircles. So when you try to do that, like take this, right? So let's take this, right? And then you have two like two semicircles with radius delta tends to 0, right? So radius is a very small circle of positive radius. I mean a circle of very small positive radius. Actually, two semicircles, and then we have z minus z naught is equal to r e to the power of I theta, and then we have dz is equal to I r e to the power of I theta d theta, and you have r is equal to delta. So essentially when we take the integral like over these two contours, so when you take, so this is your outer contour, right? So this is your outer contour, C out, and this is your inner contour. So we can divide the inner contours into two regions. One is the plus and then the minus, right? So this is plus, or this is we can call this over, and this is under, right? So essentially now what we are trying to do is when you write I over, okay, you get integral from pi to 0. So that's essentially you are integrating from pi to 0, So you are integrating from here and then here. Okay, so basically here to here, right, within the inner circle. So you are just integrating from here. So you just want to calculate what the residue of this would be, right? So then you get integral of this d theta I delta a to the power of I theta of a minus 1 by delta a I theta plus a naught plus so on. So this is the Laurent expansion. So essentially you have integral over this is the Laurent expansion of the region around Z naught. So this is the Laurent expansion around Z naught, right? So once you have this is essentially you can get this as pi to 0 integral of I IA1 plus I delta I theta a naught plus so on. So essentially d theta. So essentially what happens is this, all these terms with delta vanish. So you only end up having IA. So as expected, your this thing will be, the coefficient will be minus I pi a minus 1. So because why the minus? Because of like your it will be 0, a is equal to 0 and then minus theta is equal to 0 and then minus theta at 0 and theta at pi. So essentially it will be 0 minus I pi a minus 1. So yeah. So essentially what you have done is you have just calculated half the residue. Okay, so as we saw. Now similarly you can also do I under, which is the same thing. So this you have pi to 2 pi, which is again from integral from pi, so 2 pi to pi. Okay, sorry, wait, 1 second. So yeah, you have 2 pi to pi. So then you have a positive integral, like so you have a positive, so you have the same Laurent expansion and all that, and you can just go through the calculation. So you can just repeat the whole thing essentially, but because of the limits you have I pi a minus, right? So because yeah, wait, I think I'm mistaken here. I think it should be the other way around, because you're going from 2 pi to pi. So you're going from 2 pi to pi. So essentially it should be pi to 2 pi. So you are already you have finished the upper integral at pi, at 0. So you are going from 0 to now pi. So essentially it should be, so you have pi on top and then you have 2 pi here. No, wait. No. So okay, let me just draw the this arrow diagram here, just so that it's clear, right? So now once we fix the direction of this along the outer contour, once we fix that direction, so you see that this direction and this direction, so you can take integral of over and you can take integral. So it's like in the positive half axis, when you take the contour, you take it in the anti-clockwise direction. In the negative half plane, you take it in the clockwise direction. So essentially what happens there is your when you take this, so you're around the singularity, you have like in the same direction. You have something moving along the same direction. So your contour is moving along the same direction in that sense. So this is one thing that we'll keep under consideration, because the direction of the contour, so the direction of propagation, is directly related to the way we take our sign like our direction of contour, like the evaluation of limit. So essentially what you have then is you have this, and you can write down the Cauchy principal value as integral of f of z dz is evaluation of the half plane, the integral of the half plane. That is, you can have minus I over sorry, just I think this should be okay. Alright, so I have integral of so this is negative of the integral of over so the small region in the circle, the small circle that you're taking, minus integral of C out. So we can just label this as C2, right? So we can just label this as C out. Since we have used this convention already, let's just take this as C naught. So integral over C naught f of z dz plus 2 pi I summation of residues that are not at z naught. So any outside residues elsewhere in the contour, you'll have the summation of all these residues as well. So essentially what happens in a contour, like a singularity free contour with like just one simple singularity at z naught. So here this will be 0, here this will be 0 because Stokes theorem. So you have your principal value is equal to negative of I over. That's essentially half your winding number if you look at it. So what we spoke about the complete winding number, which is 2 pi I when you take like a singularity and then you just have one contour over the singularity, and then you surgically remove this when you surgically remove this one singularity, you have 2 pi I, which comes at the winding number. Like obviously the coefficient of the function also is there, but now once you have this, once you want to take a principal value, we essentially find out that you can split it into two semicircles, and you have one I over and one I under, and it doesn't matter which I you take. So you can have essentially like two different contours or two different principal values. So this is something that we'll just keep under consideration because it doesn't exactly reveal anything that is directly pertinent, but instead it gives you an intuition about how we take contours and how we can just slice the contours out, and like we have different winding numbers for different so the winding numbers is not only dependent on the function that you the winding number or the residue or whatever. So the residue is not just dependent on the function that you take, but it's also dependent on the contour that you take. So for example, like this gives a very interesting idea that if you have a function like if you have a singularity z0 and your contour passes through the singularity, like this is your contour, right? So then in order to remove the contour, you just need to build a semicircle around the contour. So that is basically you have half of 2 pi I. That is essentially pi I times whatever the coefficient of the function of the residue, the coefficient of the residue. So this is essentially one idea so essentially when you do this, you will end up having plus you will have I pi a minus 1 minus of minus I pi a minus 1. So it will all end up in minus I pi a minus 1 minus plus I a pi minus 1, because you are taking the other direction, right? So you will end up getting 2 pi I a minus 1. So in the end, you will get a sum of 2 pi I minus 1, because notice that we're taking we're taking completely different direction. Alright. So essentially, so one will be positive and one will be negative when you add them up, and then you will end up with the 2 pi I a. So that is the whole idea. But if you are only taking two semicircles, you have one with a plus sign and one pi minus 1 with a minus sign. So given that, okay, just keep this in mind, right? Now let's move on to the main theme for today, which is essentially the Feynman propagator, and we'll be talking about a particular problem that has to do with the Feynman propagator. Note that before we go on to the Feynman propagator, let's just note what the Weidmann function is. So this is d of x minus y, which is given by so this is essentially from the position space when you convert things to the momentum space. So in the position space, you have an object, or you have a field that is propagating from x to y under some random operators psi. Okay. So you want to measure the amplitude of this particular field, right? Some sort of amplitude. So again, it's all very abstract. So it's based on so the probability of this process of occurring of this psi field moving from point x to y is given by this in the position coordinates. When you translate it into the momentum coordinates, you have like a state, a particular like a ground state, or like any particular like a bound like any particular field of like a fixed order, and then you just have the propagator within that field. Like, so you have some sort of an expectation amplitude. It's nothing really physical. At the same time, it does give you extremely useful physics around out of it. So maybe we'll have a much clearer picture once we define the operators phi. So let's just define the operators phi of x is nothing but the integral of this is the Fourier transform, right? So in some sense, in a simple sense, right? So from the position space, you are Fourier transforming to the momentum space, and then you have 1 by root 2 omega p. So you have a frequency of omega p, and you have a annihilation operator. So obviously, when you transfer from the position to the momentum space in QFT, what happens is instead of like in quantum mechanics, what happens is you get two solutions, two kind of solutions. One is called which you call as the ladder operators. So it can either create particles or destroy annihilate particles. So you have two solutions, and then therefore like which are kind of orthogonal wave functions, right? So you have A, B, this is the annihilating operator, e to the power of minus I P dot x, plus this is the creation operator, e to the power of I P dot x. So yeah, so you have some so this is your operator, right? This is your creation or this is a field operator, which comprises of both creation and annihilation operators. So at a position x. So basically, it just says in a mathematically very general sense. So this is again, this is for a free field. So in a very general mathematical sense, it just says that given a particular point x, right, I'm either creating or destroying a particle and giving it like a particular momentum, p, right? So again, nothing meaningful exists in the integral, but the meaningfulness lies in the kind of algebraic operations that we can do, in the kind of information that we can further gather from this particular expression. So now we can define, so where your omega p for a free scalar particle is nothing but your p square plus n square under roots, right? So then you have, wait, yeah, so then you have your the Whiteman function, which is equal to integral of d3t by 2 pi q 1 by 2 omega p e to the power of p dot x minus y. So you have x, you have px, and then you have py, and then when you basically multiply them together, you get in the exponentials you get x minus y, and yeah, so that's essentially what you have, right? So now note that this is not very complete, because what you have here is, what you can define here is, you can define a Feynman propagator, which says that which actually gives you the probability of a particle traveling from point x to y. So how can you define your Feynman propagator? Sorry, is x minus y. Note that there are several things that I've done here. What I've done is like I've assumed some sort of a Lorentz invariance and all those I've made certain assumptions to be able to treat x minus y as a single variable, or if x minus y is not a single variable, and then if it is not fixed, right, if it is not Lorentz invariant, and if it is not all of that, so suppose you have some sort of curvature, or suppose between x and y and all those other kind of nonsense. So what happens here is your when you multiply when you do this, when you multiply it with like p star of y, so the term that you get here will be more complex than just a simple x minus y, right? So you will get some sort of like other mixed things, and like you will need a kind of a connection coefficient to consider the how much of x is y, and how much, like, so you're considering x and y are two independent points that are separated, and there is a Lorentz invariance between them. So everything that has to, like, there is some sort of a time like separation between these 2 points. So that is what we have assumed here. So now coming back to your Feynman propagator, you can define your Feynman propagator as a time ordered time ordered product of the operator. So what does time ordering mean, right? So it means that if I define my propagator like a particle to originate in at x, it has to and something else happens at y, right? The whole so you can't, essentially you can't have a annihilation before a creation. So you want to have the creation first. Either the particle already exists or it is created at x, and then it goes to y to get annihilated, or whatever else other interactions that you have. So essentially that is what you mean by time ordering. You want the particle, like you want everything to move in a positive time-like sense. You don't want some sort of you don't want some sort of weird ghost or something like that. right? You don't want residue, like you don't want things of the future to be appearing in the past, and you don't want all those kind of nonsenses. We want just a physically meaningful uh, setup. That means we time order these two operators, right? We say that any expectation that you have, first the particle has to be created in, and then there has to be like any other process can happen. So now to define time ordering in the simplest sense, you have T of is equal to theta of x naught minus y naught. So this is the time axis. So x naught is the time at point x, and we are considering the time at point the time coordinate of point y. So the difference, so the time-like difference between these 2 points. We'll define theta in just a second. Sorry. Plus theta of y naught minus x naught of phi px. So in a simple sense, so when you do it more, like when you go through your essential QFT calculation, what happens is this essentially means that your particle is created at x and then it is annihilated at y. Okay, and so let's just define theta before then. Theta of x naught minus y. So let's just put x naught remove x naught minus y naught. So let's just say theta of t is nothing but the Heaviside step function. So which is 1 for t greater than 0 and 0 for t less than 0, right? So this is essentially the Heaviside step function. So what happens is, so how do you read this equation now? So when you say time ordering, this is for a positive time, right? So suppose the time at the process y, the time is like positive in a positive time-like sense. So you have x happening first. So if a particle is created at x, then it can get destroyed at y, and if it is created at y, then it gets destroyed at x. So you have two orthogonal like kind of processes, or like two reverse processes. You can't have it getting destroyed at y first, so that is phi y acting first, where phi is like a creation operator, and then you can't have it destroyed at so you can't have it destroyed before you have it created. That is essentially what time ordering does, right? So the algebra of this is a little like tricky, but it makes sense in the sense that given we know what the dynamics of the whole thing is, like we are able to formulate the dynamics of your quantum fields. You also need to the only difference between the major difference between quantum mechanics and quantum field theory is just insertion of time into your three-dimensional space. So in quantum mechanics, you can have some sort of an arbitrary processes which are independent of time, and you have all of that. But in QFT, you necessarily need to bring in a space-time, which means that you have events, and you have like a Lorentz invariant or some sort of a separation between two events, like your whole like special relativistic and ultimately general relativistic picture of quantum mechanics. So that is what we want to get at. So what we want to check here right now is we want to check if, okay, so for three-dimensional case where you just have a normal field, three-dimensional field, this is not even like, yeah, you do have quantum fields, but it's just three-dimensional, three space-like dimensional. So your time ordering is completely separated, is a completely separate thing. right? So you can completely you treat time as an independent factor, independent parameter here, and you only deal with the position x and y in this particular case. Now what happens, so your ultimately your Feynman propagator, sorry, your Feynman propagator gets defined as, okay, uh, sorry, your Feynman propagator is defined as integral of d3p of by 2 pi cube 1 by 2 omega p, and then you have theta of x naught e to the power of minus I p dot x plus theta of minus x naught e to the power of I p x. So which essentially says that you have like if you have the destruction, like here it says that if you have the destruction, your particle has to be created first and at x. So if you are destroying a particle at x, it needs to be created before that, or if you are creating like, so that is the essential thing. So instead of 2 points, you're just considering one single point, and then you're just saying hey, it's created before, it has to be created before it comes to get destroyed at this point, or if it is not existing, then it has to be created at that particular point x naught at x. So that's what the Feynman propagator for a single variable is. Now in the energy momentum space, so your you have a space time. So there you have your delta of x minus y is equal to d4p 2 pi to the power 4. That's the four-dimensional Fourier transform, and then you have e to the power of I minus ip of x minus y. So you have x, all these are vectors. So and then you have I of p square minus m square plus I epsilon. So this Feynman propagator was like it was just proposed in the first when QFT started, like when was being built, it just got proposed, right? And what we had to do was we had to prove that this is nothing but this is an extension of the three-dimensional case, or like it is like a part of the three-dimensional case. In the sense, you can impose specifically Lorentz invariance given that you have you have your energy, momentum, or your force space. Of course, like what exactly the propagators are, how exactly you define this, and what is this exact Fourier transform that I'm talking about is a little like out of scope, because like I need to devote like specific time to go through all of those, because it involves a lot of like theory and a lot of like reasoning. But also another point to note here is that QFT is not like, it doesn't have very solid foundations in mathematics. So you just conjure integrals out of nowhere and conjure these kind of expressions out of nowhere, and then you expect them to work, and they do work. So it just logically and intuitively makes sense, but it cannot be formulated. I mean, it intuitively makes sense, but it cannot be formulated rigorously in mathematics. In fact, that foundations of QFT is a field in itself. Foundation of so it's like so what we do is we trust that these tools and these expressions work, and they just give you something physical about the universe, and you just go ahead with the calculation. So so the idea here is you're doing some sort of a Fourier transform, and you also have like your p square minus, you're inserting your p square minus m square, the relation, the energy shell the energy mass relation over there. So what the idea is, like, if a particle is absolutely at rest, so p square minus m square, like, if the idea is that if the particle is absolutely at rest, then you have some pure mass, that is momentum is zero. But if the particle gains but some momentum, it loses its mass to effectuate the momentum. So there is some sort of a flow between the mass and the momentum, right? So there's some again, that's why it's called the energy momentum space. So there's a flow between your energy, which is mass, and then your momentum. So typically in time, in your, if you're considering a four-dimensional space time, so your zeroth dimension is your time. So when you convert that to your energy momentum space, so instead of a four space, Minkowski space time, you convert it to the energy momentum space. The first time like coordinate get converted to some sort of an expression for the energy. So it's a matrix. So again, you have a matrix and you have a 4x4 matrix, and then the pure t part term will correspond to your energy. So the rest all will correspond to your momentum. So you have a three momentum tensor. Again, it's tensor because because of curvature of space time and all of that. But that's given that essential idea of, like, hope you have like some sort of an intuition or like some sort of an understanding of what this like integral is, right? Again, as I said, not very specific, not very exact, not very rigorous, but some sense of an intuition will do for this matter, right? So you see that so now we want to know that this whole thing, so the Feynman operator here is essentially equal to this expression. So we want to know that integral d4t is equal to integral t3t, or at least it can be reduced to the three-dimensional case. So provided that we have brought in the special theta parameter, right? We just want to know that this is essentially the same thing even in a four space-time. And we so what we do is we again so what happens is you want to write this down in terms of your d3p by 2 pi whole cube, and then e to the power of I p dot x minus y, and then now you have your 1 by 2 pi integral of dz. Okay, so this is where we bring in a complexified fourth dimension, right? So we will see why exactly we complexify it, because so you have this e to the power of I z t I by z square minus omega square t plus I, right? So you have this expression, right? So what we do here is we note that this whole thing is reduces to I by, or I e to the power of I z t by z minus omega p plus I epsilon z plus omega p minus I epsilon, right? So you are essentially factoring out. So note that and then you in each term you have plus order of e square. So e square is essentially 0. So as you are considering only an order, like epsilon is a small number, right? So essentially what so in order to evaluate the integral, so the idea is, so you have so you can't consider a point particle, and instead you consider some sort of a like we took a small section around the singularity, right? You want to consider some sort of like a small displacement, right? You want to consider some sort of a tiny number that is so that is giving you some idea for your dynamics. So it's just giving you a notion of dynamics. So just intuitively, what makes sense to me is like your I epsilon is like giving you like some sort of a room for your dynamics around that single point. So right, again, like just my intuition, but essentially now what we see this whole thing is, if you notice this corresponds to something that we worked out earlier. So we worked out earlier this thing, right? So f of z by z minus z naught integral dz is equal to, so f of z and then times 2 pi, right? So this was our Cauchy's integral theorem that we saw earlier. So now we can apply the same thing here, right? So what happens then is to give you like we'll just do the math first. Okay, so what happens then is once we apply this whole thing, we get expression of the form theta of x naught minus y naught of delta of x minus y is equal to theta of x naught. So we get two cases, right? We can break this down into two cases. One is where your singularity is at this, and the other integral where your singularity is this. Or where your yeah. So you have two cases, right? Where z plus omega p is equal to I epsilon naught, and z plus omega so z is equal to minus omega p plus I epsilon naught, or z is equal to omega p minus I epsilon naught. So you have these two. So you have two singularities for z, and based on these two, you can choose which one, right? You can kind of like pick which one. So for this, right, for the case where you have z is equal to omega p plus minus I epsilon naught, so you have this evaluation, right? So theta of x naught minus y naught integral of d3p by 2 pi. Okay, let me just write this down in the next line. Is equal to integral of so you have theta of x naught minus y naught integral of d3p by 2 pi o cube e to the power of I p dot x minus y 1 by 2 pi. So the whole integral here, right? The whole integral here, after applying the Cauchy's integral theorem, you just get minus 2 pi I e to the power of minus I z t by z plus omega p minus I epsilon naught, and this is evaluated at z is equal to omega p, right? So that is nothing but theta of x naught minus y naught. So you're just keeping x naught 1 0 up and the other 0 down, just to indicate that x naught is greater than y naught, and then you have the Heaviside step function there. So yeah, so you have some sort of, you're just selecting the x naught minus y naught contour, as we will see. So this is nothing but integral of d3p by 2 pi whole cube 1 by 2 omega p e to the power of minus I omega of x omega p x naught minus y naught me just it's not one. So when you take this exponential here, it just becomes plus I e. So this is x minus 1. Where your x and y are three vectors. They are three-dimensional vectors. That is nothing but, as we saw, theta of x naught minus y naught d of x comma y. Right? So this is the Weightman function. So now similarly, on the other end, we can prove that theta of y naught minus x naught, same propagator of x minus y, is equal to theta of y naught minus x naught d of y comma x. So what does this mean? And then finally we have your Feynman propagator without your time ordering is nothing but your time ordered one way plus your time ordered the other way with the other direction, other energy, like positive time, positive energy, and negative time and negative energy. So that is the essential idea to keep in mind here. So y naught minus x naught d of y comma x. So this gives you your net Feynman propagator when you evaluate this integral. So essentially what you found out was, you found out that an integral of such a complex form here, it reduced down to your Weightman, so your Feynman propagator of such a complex form just reduced down to your Weightman function times your time ordering in two ways, and it only matters in which way you take your time ordering. Okay, so given that we have done away with the mathematics, it's time to consider what your z is and what is exactly an intuitive picture of what exactly is happening here. So now you have your okay, let's just take smaller lines here. So this is your real part of z, and this is the complex part of z, and essentially it corresponds to your energy and time, right? Again, a very rough idea. We noted in Wick rotation as well that your real energy is complexified a complex rotator into time. So essentially when you have like a phase space for your operators, so you can cover the whole the whole like complex plane, right? So but anyways, for now let's just keep this as z, right? Like the whole complex plane, right? In the complex plane you have your you have two singularities when you looked at the Feynman propagator. One was at omega p plus I epsilon, and your other singularity was at omega p minus I epsilon. So these were your two singular points. So this is note that this is epsilon and this is epsilon, and then these correspond to your omega p and all of that, right? So, Yeah. So given this, now we have a contour integral. So we are integrating over this whole infinite region, right? But it has two singularities. So by Stokes theorem, you can just remove the uh, like you can neglect the areas where you don't have any poles, but you cannot neglect your poles themselves. So your poles leave some sort of a residue when you integrate in the complex domain. So what happens is, uh, so you can divide your integral into two semicircles, into the upper half and the lower half. So what you can do is you can say this. So you can take this to be your real energy, or a particle moving with a positive energy, and then you can say that it either moves like this. You can either take the upper half plane, you can integrate over the upper half plane. That means you can either take uh, this, or you can integrate over the lower half plane. So now notice that when you take the lower half plane, your look at the way we dealt with the single like the singularity in the previous example of the principal Cauchy principal value theorem, right? So similarly, you have a particle moving with a positive energy. So you have the contours taken along a certain direction, and when you do that, you essentially end up getting a singularity. Like you essentially either end up getting plus omega p minus I epsilon. Sorry, this is minus omega. This is minus omega p plus I epsilon, or this you get omega p minus I epsilon. So you get particles. So when you take the contour integral, and you essentially end up dividing the contours into two halves, right? Your upper half and lower half. So the idea here becomes, you have a particle, so to have positive energy particle, so you can only have positive, and if you have a particle you can have only positive energy, whether it's a particle or an antiparticle or whatever it is, you just have a definite positive energy. You cannot have something called as a negative energy. You can't like just lose out energy from nowhere, right? In the sense that you're like a particle has to be created first, and it has a form of energy, has to condense or manifest first. So given that principle, so when you are moving in the positive energy direction, right, uh, when you have a a particle of a positive energy, so you can take your contours only along this kind of your along the direction of positive energy, and that means that you can divide your contours into two parts, one with negative frequency or with positive frequency. So with negative frequency, it moves in positive time, and with positive frequency, it moves in negative time. So if you look at the direction of the arrows here, right? So this is this and this is this. So with negative frequency, it moves in positive time, and with positive frequency, it moves in negative time, which is essentially, when you reinterpret it in physical term, you have a particle of positive energy or positive like frequency moving forward in time, or you have a particle of negative frequency moving backward in time, right? Negative energy moving backward in time. Again, like the notation of like where exactly you have positive frequency and negative energy and negative frequency is based on like how your conventions are long back. So typically you consider like the flip, the ulta sign. So like, so again, like it's a matter of conventions, and you need to set up the conventions like long when you start building your quantum field theory. But essentially the idea is once you have time ordering here again, and your time ordering comes out not in terms of imposing a superficial time ordering operator in the three-dimensional space, but it arises naturally when you take contour integral, when you complexify time time and then take the contour integrals over that. So when you take contour integrals, you can take two types of contours specifically, and note that this is a choice that you have made, right? This is like some sort of a choice we have made. Of course, it is perfectly fine and logical to take this sort of a contour, or you can take some sort of a contour which includes both, like both the singularities. But in order to, like, when you evaluate this particular denominator, and when you reduce it down to this particular form, you are essentially taking the contours to, like, you are essentially simplifying the contours to the red and yellow contours, like you can upper half and lower half planes. So this is the essential idea. Of course, like with quantum field theory, anything with PFT is like, it is to a certain extent like I wouldn't say ad hoc, but it's a little bit of hand waving, or at least in term, like when you try to explain it, it becomes extremely hand wavy, because there is because there is quite a lot to set up and deal with in the first place. And but the idea here, I hope that is clear, like where exactly. So if you look at it in terms of like your integral, and if you don't try to interpret it, it's very simple. You just have this integral breaking down, and then you have two singularities, you have two poles, and based on your pole, you're eliminating you're eliminating one of the poles, and you're keeping the other. So you can't have z for both values simultaneously. So you want to select z in such a region that, like, you can you can just like have you can just pick two separate distinct values of your like your complex number variable, right, here in this case. And therefore you have your plus omega p minus I epsilon naught, or you have minus omega p plus or I epsilon naught. So you have two distinct cases, and for each case you evaluate, when you evaluate your integral using the Cauchy's integral theorem, you have two singularities and you have two residues. So you have to consider particles moving with a positive frequency and with leaving a particular residue, plus particles moving with negative frequency and leaving a particular residue at the end of it all. So that's essentially it. And this is something that is like so I mean, it's something that is very it's kind of very confusing, because different people have different ways of explaining it, and different people have it's still a little hand wavy, and there's still a room for interpretation, and people choose to explain everything, or people choose to leave some things out. Based on that, there are a lot of interpretations based on to how you do it. But the idea that I wanted to give here is that when you calculate your singularities, and when you want to surgically remove your singularities, or if you want to evaluate the residues or singularities, it gives you some sort of a value around that, right? And this value is nothing but the presence of a particle. So you're given some sort of an expression for the presence of a particle at your singularities when you consider complex function. So right, it's like very simply saying when you have a charge, your electric field at the point charge becomes infinite, or your electric potential becomes infinite at that point charge. So so using these infinities and to like talk about their dynamics, and to instead of approximating this, so what we do is we just like give some sort of dynamics to these singularities, and that is essentially how your whole field theory emerges. So right, and how can you talk about singularities and still have something that is analytic? By complex analysis. So that is essentially the idea that I want to like. This is one of the key roles that complex analysis plays in physics. Apart from this, there is also the matter of continuation, analytic continuation, and of course, when you have real uh, continuation, it like complex continuation is much more powerful than real continuation, as we saw, right? Because it has some reduced simplicities in the form of your Cauchy-Riemann theorem, or your the Cauchy's integral theorem itself, or whatever it is. So you have, because of all these interplays and because of like the complexification, the relation between like your complex number and the real numbers, because of all that, right, you have some specific interplays, and that reduces their whole subject and makes it much more appealing. So yeah, so essentially, right, so for any sort of a calculation in some sense with your singularities in physics, you tend to rely on complex analytic methods. So you just take a variable and you complexify it, and then you see how it can be analytically continued, or it can be integrated, or it's differentiated, or whatnot. So that is essentially the idea, or the central role that complex analysis has to play in physics. And I think with that, yeah, we'll stop the recording for today.